Welcome back, Mindsetters. I hope you're nice and ready, because I'm now, you know what, I'm actually tired of saying this, that I'm always excited, but I genuinely am today, because we're going to be doing some pretty crazy stuff. As you can see, Phil is in his crazy scientist suit, you know. So, I want to know what's happening. Phil, fill us in.
Oh, absolutely. Okay, tonight we're taking a look at a little bit of grade 11 redox chemistry. So grade 11s and matrix, we're going to be carrying on the redox. We're going to be doing some exciting experiments, getting you guys in on an act, perhaps doing a few FET experiments if we get a little bit of time.
Right, that'll be cool.
There's some pretty cool stuff going on.
Right, awesome. So guys, you know what to do. Make sure you stay tuned. Make sure you're watching, because there's a lot of exciting stuff happening. And I still have a calculator and a labeler to give away. And I will actually be giving those to you guys just now. And guys, you know the page, www.facebook.com/learnextra. Get to me, get chatting, tell me what you guys are thinking. If you're lost anywhere, if you need help, you need to tell me, so I can get those questions to Phil. And as always, there's a monster challenge question from Mr. Phil over there. So I'm actually going to do best, and right now I'm going to hand over to Phil. Phil, take it away.
Absolutely. Thank you, Ty. Okay, well, one of the first things that I wanted to show people, and I wanted to make sure that people actually understand why we're doing this, is because we need to know how redox happens, and we need to see some evidence of it. And tonight we're going to be taking a look at some electrochemical reactions. Now, the first one which I'm actually going to show you is probably the simplest electrochemical reaction. It's a reaction with a metal, with a non-metal, which I'm actually breathing in at the moment. So I've got a heat source over here, the very nice hot burner, because you can't just do this with a lighter. As you notice, I'm wearing some protective clothing here. I hope I don't burn the studio down. But I've got a little ribbon of magnesium metal over here, and magnesium metal combines with oxygen in a redox manner. Now, what redox means is that they're going to swap electrons, and something quite exciting is going to happen. So we're going to get this metal burning, and magnesium is known especially for this. It does take a little while to get going. There we go. You can see that incredibly bright light. You can actually see the redox is happening right in front of you. So what happened was that magnesium reacted with oxygen inside the air, a redox reaction happened, and we were actually able to witness it. I've actually got the product here, that's magnesium oxide, and that's quite cool. And I'm going to turn this off for the moment, and I think we're going to get started with the lesson. What do you think, Ty?
I think that'll be awesome.
Okay.
I'm slightly a bit blind from that, but my eyes are adjusting right now. Like, that was really, really bright. And that's the reason why I'm sitting on this side of the table, because I'm not trying to, like, everyone knows that Ty's got long hair, you know? So long hair next to an open flame is never, ever a good idea. That's why I'm staying far away from Phil in his mad scientist suit.
There we go.
Because I'm just thinking, whew. Could you imagine all my dreadlocks on fire? That's a reaction no one wants to see. But for now, I'm going to hand back to Phil. Phil, good to go?
Okay, well, absolutely. Okay, well, we're going to get right into it. This challenge question, which I'm actually going to ask Ty to post up, is all to do with redox. It's all to do with predicting the products. Now, earlier on, I took magnesium and oxygen, and we put them together. Now, I've done this many times before, and I know what the products are going to be. But I want to teach you during this redox lesson on how to predict your own products. So what I'm going to do is I'm actually going to show you this challenge question. There it is. Okay, my challenge question says, which one of the following will be products when magnesium chloride, remember that's a salt, is placed in an electrolytic cell? Okay, so magnesium chloride is placed in an electrolytic cell. I will give you guys a little bit of a clue. I'm not that mean. So what I'm going to be doing is I'm just going to give you a little bit of a hint, is that an electrolytic cell also contains, and let me actually put this in a color that you can see, because I know that red's not so great. Okay, so an electrolytic cell means that I've got MgCl, which is aqueous, which means that it's dissolved in water. And that's all I'm telling you guys. I want to see if you guys can figure out if it's magnesium and chlorine as your products, or if it's Cl2 and oxygen gas, or H2 gas, Cl gas, and some MgOH2, okay? MgCl2 and H2O, okay? Quite a challenging question, okay? One of the things that we actually managed to pick up a little bit earlier was that people are not actually understanding their redox particularly well. So we're going to put it up on the page, we're going to come back to it, and we're going to see if everyone understands this. So you've got a few options. Option A, which is magnesium and chlorine as products. Okay. Option B, which is chlorine and oxygen. Option C, which is hydrogen, chlorine, and magnesium hydroxide. And then option D, which is MgCl2 and H2O. Okay. Well, Ty's posted up that question. I can see he's hard at work on the Facebook page. Let's start with our question. Okay, today we are starting to talk about electrochemical reactions. Okay, so let's just put this up and see what we're talking about. There we go. Okay, All right, now, particularly, all electrochemical reactions are talking about the movement of electrons. Okay, now, for matrix, this is going to be very, very familiar for you. So electrochemical reactions are all about the movement of electrons. Now, every time I start to talk about the movement of electrons in a reaction, I am talking about a redox or a redox reaction. It depends on how you say it, but redox is the section of chemistry that we're talking about. We're talking about reduction and oxidation. Now, if you don't know what those are, or if you don't remember what the grade 11 definitions of reduction and oxidation are, that's absolutely fine. Just remember in this first part of the show, we're actually going to see what is happening inside redox, what is reduction, what is oxidation, how do I put them inside cells. Okay, so there it is. We're going to be talking about our electrochemical reactions, and they involve the movement of electrons. So again, that two-part word, reduction and oxidation, there it is. Let's get into our lesson, and let's just skip past our challenge question there. I hope you're working hard at it. Now, what I'm going to start talking to you about, first of all, is I need to discuss where redox chemistry actually happens. I showed you an example a little bit earlier where I was taking magnesium and oxygen and I was making magnesium oxide. Remember that that is an ionic compound. Okay, so ionic compounds. Just remember that ionic compounds actually account for a huge amount of the chemistry that you guys do. Okay, ionic compounds, very, very important. I just want to remind you guys what an ionic compound is. An ionic compound sometimes is called a salt, and we're actually going to be dealing with a little bit of a salt sometime later inside the show. We're actually going to be talking about the electrolysis of salt and seeing what happens when I take table salt and I play around with it and do some chemical stuff to it. Now just remember that a salt is made up of plus and minus ions. So those are cations and anions, if you remember those terms. Okay, now the first thing which I'm going to do is I'm going to make a copper compound. Okay, so here it is. I'm going to take copper metal and I'm going to change it into a new compound which needs Cu2+. I'm going to make a positive ion. Now one of the things that people don't understand is that to make a positive ion, I actually need to take something away. And those are electrons. Okay, now I'm going to show you something which confuses a lot of people. I'm just going to move this out of the way. Here's a reaction which you might have seen before. I can take copper and I can change it into Cu2+ and 2 electrons. There it is. Okay? Now, I noticed that copper 2+ over here and the 2 electrons over here, they actually balance each other out. Now, the question is, how can I be losing an electron when I see plus electrons? Just remember that when I've got the electrons as products, that means that they are coming out and they're being set free. So this means that my electrons are out. That means that they are being lost. So to make something more positive, I have to lose electrons. There it is. If the electrons are on the right-hand side, that means that there is an electron loss taking place. Okay, so one of the important things that I'd like to point out, just as a little bit of revision, let's see if we can find it. Okay, all right. So if I've got copper 2+ and copper 2+ has lost those 2 electrons, I call the loss of electrons. Remember that my loss is called oxidation. Now, I'm going to show you a little easy way to remember that a little bit later on in the show. But the loss of electrons, copper is being oxidized. That means that it's lost the electrons. So the loss of electrons, and if I've lost my electrons, there they are, I have undergone oxidation. Now, you might ask yourself, where does this word oxidation happen? Or where does it actually come from, and why does it sound like oxygen? Well, this is what oxygen actually does. Oxygen goes in there and grabs electrons. It makes things lose electrons. So if I treat something with oxygen, just like the magnesium over there, what I'll actually notice is that the magnesium has lost electrons to the oxygen. So therefore, oxidation is the loss of electrons because that's what oxygen did. We don't always have to have oxygen involved. In fact, in this example, in order to get copper to change into copper 2+, I'm actually going to use a different compound. I'm going to be using copper bromide in this case, and to make that, I need Br. I need bromine as a liquid. Okay, well, let's take a look at the next slide. Let's see how bromine is going to do that. I've made my copper 2+ ions, and let's see what else goes on inside there. Now, bromine, on the other hand, has got to do something very different. Remember that bromine is a nonmetal. Nonmetals really like to take electrons, and I see them over there. I can see that these electrons, because they're on the left-hand side, I can see that they are being gained. I'm taking these electrons in, and they are becoming mine. Okay, so what's actually happened over here is that bromine plus these 2 electrons has actually made this negative ion. That's what nonmetals usually like to do. There are a few exceptions, and you can make some nonmetals into positive ions. Very unusual, especially for things in group 7. There's only one other element that can make group 7 into a positive, and that's oxygen. Doesn't happen very often. But now, bromine has taken on 2 electrons and has now made a bromide ion. It's taken them on, it's become more negative, and I see a little bit of a clue over there. There we go. Something else. The key to a good redox half reaction, and the reason that this is a half reaction is because I'm not showing anything else. Now, the key to it is to make sure that the charges on both sides are still the same. So bromine and 2 electrons, I can see that there are 2 negative charges over there. If I take a look on the right-hand side, I can also see 2 negative charges. So if you're making these from scratch and you're actually in grade 11, how do I know how many electrons to put and where to put them? I need to make sure that the charge on the left-hand side and the charge on the right-hand side is exactly the same. But that's not why we're looking at this reaction. I'm trying to see how to make bromine minus ions, how to make copper 2 plus ions. And what I actually notice is that electrons are being gained. So if I gain electrons, what am I doing? I'm doing the other half of redox. I'm actually doing reduction. Okay, and that's where my word comes from, redox. Reduction and oxidation. So there it is. So reduction is the word. Okay, now this word reduction is a little bit more difficult to understand without going into a lot more theory. But for those of you that have studied this already, reduction refers to the oxidation number. When the oxidation number goes down, that is a reduction. That's what this word means. It means to take things down. When the oxidation number goes down, that is a reduction. And the only way I can take an oxidation down is by gaining electrons. Okay, so now I've managed to figure out where red and ox come from. Okay, so ox is the loss of electrons, and reduction is the gain. And I'm fairly sure one of your teachers has actually taught you this really nice trick. You can actually write out the words oil rig. If you can't remember which one is which, if I write out the words oil rig, what I'll actually find is that oxidation is the loss, there it is, and that reduction is the gain of electrons. So it's a very nice way to remember which one is oxidation, which one is reduction. Okay, so we've done a little bit of oxidation on copper, we did a little bit of reduction on bromine. Let's see where all of this leads us. Now, most redox reactions are actually a little bit more complicated than just taking the 2, usually a metal and a non-metal, sticking them together just like we did in the studio. So instead of taking magnesium and oxygen, which would have also been a redox question, what I'm actually finding in this case is that I've taken copper and bromine, and that's fine. But now, most of the questions inside redox actually consist of slightly more difficult questions. And the question is, how do I know if chemicals actually react? And this is what I'm talking about. This is where this lesson is going. I'm going to be talking about this guy. How do I tell if a reaction is spontaneous? Now, that's a very difficult to understand word. Okay, spontaneous means that it happens without any help. That means that it's going to happen without any energy. Okay, so the word spontaneous, that means that it happens without help. Okay, without energy specifically. So I don't need to go into there and change any of the things or add any energy or do anything of the sort. It happens without any energy added onto it. So spontaneous, if something spontaneously happens, that means that it's going to happen anyway, and I don't need to help it along its way. Okay, so that's what a spontaneous reaction is. Okay, now there is a way to figure out if things are going to react spontaneously in an electrochemical way. And that is by taking a look at the table. And I'm going to be very, very careful about how I actually take a look at this table. Okay? Now, what I'm going to do is I'm going to study the steps on how to do a good redox reaction. There it is. What we're going to do is, before we even look at the table, we need to know what we're looking for. Okay, so there it is. Step 1, it says identify the chemical on the table. I'm going to show you how to identify it and how to identify the right ones. So that's not too difficult. And then what I'm going to be doing is I'm going to be picking the best reactants. Okay, so there we go. Step 1 is to identify. So that's definitely your first step. If you guys are taking notes, here are the keywords. Identify and pick out the chemicals. Now that might seem simple. All you're doing is you're looking up and down a redox table and you're saying, okay, there it is, there it is, there it is. I'm going to show you just how tricky it can be. Okay, now pick the best reactants. Now this is not the one that you like, the one that's your favorite color or anything. The table actually tells you which one is the best. So I'm going to show you how to pick the best reactants. Now that's definitely something worth noting. The best reactants are going to be the ones which actually do the job for us. Okay, next in line, let's just see if we can bring up our next one. There we go. So it says write out the reaction from the ones that you've chosen. Okay, now this needs a little bit of a note. Okay, the ones which we've chosen as well, these guys are the best ones. The best ones that we were talking about in step 2, these are the best ones for the job. And we're going to figure out which ones those are, and I'm going to show you how to pick those off the table and how to actually work with those. So when I write out my reaction from the ones that you've chosen, that's where you start. Okay? So this is what I'm talking about. This is the start of my reactions. Okay? And that's where we begin the line. And then our fourth step, let's see if we can bring that up. There we go. Then I've got to do the very, very last thing. Lots of people jump straight to this. And the important bits to notice there is that I've got to balance the electrons. And balancing the electrons is quite important because redox is all about the electrons. It's all about the charge, making sure that the charge is in the right place. Where did it go? Where did it come from? And I've got to make sure that I balance those electrons before I do anything else. And that anything else is to add the reactions. That's pretty much, I mean, it could be step 5, but it's pretty much a formality. If you're balancing the electrons, that's all you're doing. So let's just go through these steps quickly. I've got to identify, then pick out the best reactants, then I've got to write out my reactions, then balance the electrons and then add them together. That is the very last step. People tend to go for the last step because that's where the answer is and they think that's where the marks are. But now what I can actually tell you is that without step 1 and 2, step 3 and 4 are absolutely impossible. I can tell you now that redox really doesn't have to be complicated. It's very, very easy when you follow these steps. So identifying and picking the best reactants, these two are actually the most difficult, but by far the most important in these steps. Okay, so I hope that you're with me on that. So identify them, picking the best reactants, and then writing them out off a table. I'm pretty sure that everyone since like grade 2 or 3 can actually just copy something out. Okay? And that's all that step 3 and 4 are actually all about. If you can do very, very simple maths, and if you can copy things out, step 3 and step 4 are going to be your friends, and they're going to get you your marks. These can be 6 to 8 marks each. So these are very, very important questions, and we're going to be starting to deal with them fairly soon. Okay, how are we doing for time there, Ty?
I think we might need to take a little bit of a break just now.
Okay, all right. Well, I'm just going to cram in a little bit more knowledge. I promise I will stop and slow down soon. There's just so much cool stuff to get through, and I want to get through to another experiment if I've got the time. So there we go. Let's just make sure we can actually get through there. Okay. Now, this actually deals with something which we were talking about before the break of the show, before the break of the grade 11 show. We were actually trying to figure out which one of these two combinations would react. Now, you might wonder why your science teacher gets all excited to say, okay, well, don't mix that and that because the science teacher knows what's going on. Now, the way that they know is because either they've done this experiment before and it's blown up in their face or something, or they got it wrong, okay? But they can be smart about this, and you can as well. I want to figure out which combination is going to work. Either copper metal and zinc sulfate, which is aqueous. I'm going to make a few notes on that. Or zinc metal and copper sulfate. Okay, now, they might look like exactly the same thing, but the devil is in the details here. I want you to take a look. Right, now I want you guys to discuss why one of these reactions is going to occur and why it's not. And we're almost going to go to an ad break, but what I'm going to do is I'm going to set you up for success on this. I'm just going to give you a little bit of a hint. I want to make sure that people are finding the right things on those redox tables. And I think Ty's actually posted up a couple of the samples of the tables which I'm going to be using, so you guys can do this with me. I'm pretty sure that it's small enough that you can actually pick this up on a cell phone screen as well, so if you're following us on a cell phone, that's great. There's 2 redox tables which we've posted up to the page, and you can actually follow us and work with us. Okay, So copper metal, copper you can find exactly as it is on the table. That's great. But now zinc. I can't go looking for zinc sulfate on that redox table. What I'm actually going to start taking a look for is zinc 2+. You cannot find zinc yet. I'm going to be finding zinc 2+. Now, some of you might say, okay, well, how am I meant to guess that it's zinc 2+? Well, zinc has a valency of 2+, and that's from grade 10 chemistry. Now, the other ion, which you're going to find, that is a potential reactant, is SO4 2-. So I want you to go find these three things. So copper, zinc 2+, and sulfate ions. In the right-hand reaction, I've got zinc and copper 2+. Now that's the difference. In this reaction, I've got copper 2+, and I've got some sulfate ions. And if I get my way, we're actually going to do this chemical reaction in the show, but it's not going to make a bright light, and it's not going to blind you guys completely, and it's not going to make any bangs or pops or whizzes or anything like that. But I want you to take a look at these two reactions. Can copper react with zinc 2+, or does copper 2+ react with zinc? And I want you to figure this out using a table. But I think I've talked enough, and I think it's time for that ad break. What do you think?
So, guys, I know this is a lot of information. But just make sure you take a nice little break, grab some snacks so you don't have to get up. You can just pay attention, because there's a lot of stuff going down, and I'm still looking at this challenge question, and it's even making my head spin. But for now, guys, we're going to see you after this break. See you soon. Welcome back, Mindsetters. I hope you had a nice little break. For me now, I'm sweating a bit right now because I'm a little nervous because Scuba Steve Phil is behind the desk about to do another experiment. So I'm going to keep my distance because I'm not trying to catch on fire or die from noxious gases. But guys, make sure you're paying attention right now, because besides just the fact that this is extremely dangerous, always wear safety gear when you're doing experiments, and even better yet, make sure you do it at school with teachers' supervision. And I just want to send a quick shout out to Kashifa's mom, who allowed her to actually hijack. Can you believe this? Like, Phil, Kashifa's mom allowed her to hijack her Facebook so she could actually make sure she's on the page for this experiment. So guys, I'm just saying, I'm looking at this, I'm just like, I'm going to make sure I sit here. Because this is where I'm staying. But guys, make sure, if you're just excited as I am and you know what's about to happen and you can keep follow with us, make sure you get on the page and keep chatting with us, because I'm also just posted up the redox pages. So guys, there's stuff up for you, so download it, use it, it's for you. And Steve, Phil, we're good to go.
Absolutely.
I've got to stop calling you Steve.
Oh, that's okay. I can be Steve today.
Again.
Okay. Well, we're going to get the fire and flame out of the way. What we're going to be doing now is I'm going to be taking some zinc sulfate. What I've done is I've actually dissolved some zinc sulfate, and we're going to be adding a little bit of copper powder to that. And I'm hoping that you guys can actually see some of this color. I'm going to hold this over there, and I'm actually going to hold this in front of my lab coat so that you can actually see. I've got some brown powder over here. And what you'll notice is that when I stir this copper powder in, I can see that this brown powder, this brown powder over here, nothing really all that exciting is actually happening. I noticed that when I put copper inside zinc sulfate, very little happening, and I actually noticed that the brown powder stays brown, and that's not very cool. Okay, so I like chemical reactions, there's very little happening, and I'm actually going to prepare the second experiment, and we're going to see what happens. So brown powder stayed brown, nothing exciting. I'm going to put that down. But now the second experiment, this is where I'm going to bring your attention to. Now, this stuff over here is copper sulfate, and here is my zinc powder. So what we're going to be doing is I'm going to be putting some copper sulfate inside this here beaker, and I'm going to be stirring it in. Now, I'm pretty sure that you'll actually see. I've actually got a blue spatula full of these crystals, these wonderful copper sulfate crystals. When I put them inside the water, I start to notice something quite interesting. Now, this is one of those few experiments where you can actually see something happening. So I see this blue color, and its blue color is slowly making its way through the beaker. And as I actually stir this, I'm dissolving the blue crystals. I'm allowing the copper 2+ and the sulfate ions to go their separate ways. I'm freeing them to move around and react when we do react them. Now, this is just another one of those chemical precautions. what I'm going to do now is I'm going to use a different spatula. Now, if they ask you why I'm going to be using a different spatula, this one is nice and wet. It's contaminated with copper sulfate. So I'm going to put that down for the moment, and I'm going to get a nice, fresh, dry one. Now, over here, I've got zinc metal powder. And what I want you to see is that zinc metal powder initially has got this dull gray appearance. Now, I'll actually see that this gray appearance is not all that exciting, and I can actually see that it's a normal metal color for a powder. Okay, so what I'm going to do is I'm going to add this powder inside here, and we're going to see what happens when I put zinc sulfate powder inside a copper sulfate solution. Now, initially, all you see is the powder color, and I can see that it's gone nice and black over there, and that looks kind of great. But something should start happening when I allow that to settle out, and it should settle. We might need to leave that for a little while, but what I'll actually start noticing is that zinc actually changes its color. And I've actually started noticing, I'm not sure if you can at home, this has started turning a little bit brownish, just like the copper powder. So what I suspect has actually happened is I've had zinc powder change into copper powder, which is actually impossible. I can't change zinc into copper. The zinc reacted and was replaced by copper. So what actually happened was the zinc went into the solution, took the place of the copper 2+, and actually kicked out the copper to be on its own. Now, I can actually start to see that on the bottom here, I'm not sure if you can see this, but I've actually got a very nice brown deposit starting to form, and I'm actually going to let this settle. And as the reaction goes, I'm going to come back to this a little bit, and we're actually going to see what happened. Where is the blue color? Why is the blue color gone? Why is there a new brown color happening inside this beaker? Okay, it's starting to settle. I'm actually going to leave that to settle down there, and I think we are going to let that settle for a moment, and I'm going to get back to my lesson. So, okay, so Ty, how's that page looking?
Well, the page so far is lighting up, actually, because all the mindsetters are dying to try and find out what the answer to the challenge question is. So I'm getting the usual A, B, no, C, no, wait, no, go back, no, I think it was B, no, but wait, it's A. So guys, mindsetters, as I always tell you guys, we need the full answer and explanation. Because guys, as I keep telling you guys, this is for study notes. It's for you to go back to refer to if you're lost anywhere, if you need help. So guys, make sure you keep posting and keep chatting to each other. And if someone's lost, if you see someone, if you know the answer to something, answer it for someone, because they need your help too. But for now, I'm going to hand over to Phil. Phil, take it away.
Absolutely. As you see, I can change out of these things very, very quickly. Okay. All right. So now what I wanted to just bring some attention to was that one of these reactions happened and one of them didn't. I noticed initially when I took some copper and I placed some of this zinc sulfate inside there. Let's just bring that back. So zinc sulfate and copper, there was no reaction. And I'm actually going to cross this out. I'm going to show that there was absolutely no reaction. The brown stayed brown. Absolutely nothing happened at all. However, this other experiment, when I put zinc and copper sulfate, I put these together, what I actually found was that was spontaneous. And that's fantastic. Okay, that's what I'm looking for. Spontaneous reactions are ones which are going to happen, right? And they did happen. We saw them happen inside the lab. I saw the zinc disappear. I actually saw the blue color of the copper disappear as well. Now the question is, how can I predict this using a redox table? Now what I've done is I've taken two very small parts of the redox table, and I'm hoping that my producer actually puts this up on the screen, because I want to show you how to use this amazing tool. Now I've shown you a piece from the top and I've shown you a piece from the bottom, and I'm going to show you how to calculate this. How do I know that zinc and copper 2+ react in a spontaneous way? Well, here it is. I hope that you've got a table in front of you, or you've taken one of those tables that we've put up on the Facebook page, and you're going to be circling with me. I want you to have a highlighter or a pencil in front of you, and we can actually do this, and I want you to do this in your exam. This is the best cheat sheet ever. They give you one of these in the exams. If you know how to use it, redox is easy. So what I'm going to be doing is I'm going to be studying why zinc and copper sulfate react spontaneously. Here it is. So let's start taking a look. I have got zinc. Now, what I've noticed is that people really struggle to circle the correct one. Why did I not circle zinc 2+? Why did I not circle the whole reaction? Be careful that you only circle the ones which you actually have. I had zinc metal, and let's actually bring it over there. I actually had this stuff, zinc metal. And zinc metal is not zinc 2+. Zinc metal is Zn. I've only got Zn. I don't have the whole reaction. I don't know which reaction I've got. Okay, but let's take a look and let's see what else was inside this. What else did I have? Well, one of the other things which I had was copper sulfate. And I've actually taken a piece of the table which has got copper and sulfate ions on the page. So let's go to that. Let's see what we've got. Okay, I told you that I had copper sulfate. There it is. Cu2+. But now I see that there's Cu2+ as well over there. And to make things even more complicated, I've got a sulfate ion over there. But now I'm going to show you something. There's something else in the sulfate which I don't have. I don't have H+. So what you'll actually notice is that you can't choose ones which don't have something that you don't have. I did not tell you that the solution was acidified. I would need an acid to make H+, and I don't have that. So what I'm going to do is I'm going to cross this one out. It's not even a potential. It's just going to sit there and watch. Okay, so the step 1 is complete. I've chosen my reactions, or at least I've chosen the species, or I've chosen the chemicals which could react. I saw that I had Zn, I saw Cu2+, I saw Cu2+ again, and I circled both of them. Now what I'm going to do is I'm going to pick the best guy for the game. Now, you've got to pick one from the left and one from the right. So how do I choose this? Well, the examiners have actually made this really, really easy for you guys. They've actually put arrows pointing which direction to choose. So I've got to choose between these two. Okay, so let's do that. I can choose between the top reaction, or I can choose between the bottom reaction. But look at the arrow. The arrow is pointing downwards. So what it tells me is that I've got to choose the lowest one on the left-hand side. There it is. Okay, so there's copper 2+. I'm going to choose that one. This is the man for the job. I'm going to circle that very nicely. Let's even highlight him. Make him feel important. There we go. Copper 2+ is the man for the job. On the right-hand side, I don't have many choices. This is the only choice. I've only got zinc. So the ones which are highlighted in yellow are the ones which I choose. So step 1 was to find them on the table. Step 2 was to pick the best one by looking at the arrows. Now, if I had a choice between a couple of these, I could actually go, okay, well, which one, and choose the highest one. But over here, there we go, zinc and copper 2+. Now, here's how you tell if something is spontaneous. I actually decide, I say, well, is there going to be any reaction between these? Yes, there absolutely is, because you guys can do this at home. If you can draw a line between your two chosen reactants, and that has got a positive gradient, in other words, it means pointing up when I look from left to right, that means that we have a spontaneous reaction. So let's write that in. That means that I've got a positive gradient. Now that means an M value, or whatever you want to call it, so it's a positive slope if you want to call it that. That means that that is going to happen, and it did. So that means that this is spontaneous. And we actually saw that the reaction did take place. A spontaneous reaction is one which happens without me getting involved. Okay, now what I want to show you now is what's happened to our reaction. Remember that this was blue. What we actually notice, and let's actually bring this up in front of something blue. Okay, there we go. Let's make a nice white background. You can actually see that the blue color has gone out of this. This was a very nice, lovely blue color. And what I'll actually notice at the bottom here is I can actually see a mixture of the gray, which was there already, but there's something brown inside there. There's a brown material sitting at the bottom here, and that is copper metal. So what I'm going to do is I'm going to try and explain what happened here. This was definitely spontaneous. I threw in this gray powder. The blue color vanished, it disappeared, it went away. Now let's try to figure out how to work with this in terms of redox. Okay, so let's put that down for the moment. And let's go back to our table and let's try and explain what happened. So step 1 is complete. Step 2 is complete. Now what I've got to do is I've got to pick which direction to write these reactions in. Now watch, this is so easy. There's actually only one way that you can do it. If you've done step 1 and 2 right, all that you have to do is write them going across the table. So let's start with zinc because it's on the top. I noticed that if I start with zinc, I need to start from here and read it in that direction. That means that I need to read it going across to the left. So I start with zinc. Let's actually write that down as we go. Let's make a little bit of space over there, and let's just copy it out straight off the page. So let's do this together. Now, everyone seems to miss out a few pieces. I knew that I threw in my zinc. I have to start with it. That was my chosen reaction. You no longer use the double arrows because we've chosen a reaction and we know which direction it's going in. It's not reversible anymore. So Zn goes to make Zn 2 plus 2 electrons. Now, I get a mark just for copying that out. That's amazing. Now, the only thing which I'd like to do at this point is figure out, is this oxidation or reduction? Well, if you remember what I said early on, zinc has to lose electrons to become a positive ion, just like copper did. So if the electrons are on the right, that means that there is a loss of electrons. So this must mean that this is my oxidation half reaction. Okay, but what about the other piece? Remember that half reaction is not a whole one. So let's figure this out. Let's actually take this out of the way. Let's make sure that we can actually see our redox table. Okay. Now what we're going to do is we're going to take a look at the other guy which I chose, and that was copper. So there it is. Let's start with copper 2 plus. There it is. I chose it. Now I need to write it going across. So I start with the one which I choose, and then I move from there. So I see that I've got copper 2 plus, and copper 2 plus added 2 electrons. There it is. And that went to make copper, as in copper metal. Now, I just want to make some notes on this, because this is something that you're actually kind of expected to know. And I'm not sure which textbook actually tells you, so it might be worthwhile to say it here. But copper 2 plus is blue. And copper metal is brown. So that's quite amazing to me, because what I actually notice is that I've taken blue stuff which was dissolved, and if I take a look, I don't have any blue stuff anymore. All that I've got is this brown stuff down at the bottom. I'm not sure how well that's coming through on the camera, but there's this brown stuff at the bottom. I've actually shown that I've taken ions and I've made them into a metal, which is quite amazing. I've actually done some chemistry very, very simply. I took blue ions and changed them into brown, and I actually saw the redox happening. So this was step 3. Step 1 was to find them. Step 2 is to choose them. Step 3 is to write them. And step 4 is actually probably the easiest one. All that you need to do is you need to say, okay, well, I need to make sure that the same amount of electrons is in the oxidation reaction. And let's actually label the other one while we're at it. So here is my reduction half. I need to make sure that the same amount of electrons are going through both reactions. Lucky for us, they are. If they're not, you need to find a lowest common multiple and multiply them up. But luckily, I can say, okay, well, there are 2 electrons out on the right-hand side, 2 electrons in on the left-hand side. Fantastic. Now what I'm going to do is I'm going to put them together to get my marks. So let's just draw a line, because we're adding our 2 reactions. Let's make a little bit of space to get our marks and hopefully pass my exam and get an A. Okay, so now I need to add everything on the left-hand side. All the reactants need to go together. All the products need to go together. So let's do that. I've got zinc, and zinc reacts with copper 2 plus, and that's going to make, and you'll notice that I didn't write in the electrons from the left because we cancelled them out, and that's going to make zinc 2 plus, and there is our copper metal. I can actually see the copper metal. Okay, so that's fantastic. What I've actually done is I've predicted a reaction, I found the half reactions, I found the net ionic reaction, and something else which I just want to point out quickly is that sulfate didn't participate. That means that that is called a spectator. A spectator is somebody who watches. So a spectator ion, it did not play a part inside the redox. Sure, I'm tired of talking. I think it's time for a little bit of a break. All that chemistry has made me a little bit dry in my mouth. I need a little bit of a drink.
A little bit of water.
I think so, and the
There's
mindset is at
definitely an
home.
assortment of juices there.
I don't think I'm going to be drinking any.
All right. So, good for an ad break?
Absolutely.
All right. Awesome. So, guys, you know the drill. Make sure you get to the page, chat to us, send in those questions. And by the way, we had a special request that came in.
Okay.
Like, her name is Kausum, and if you could just say hi to her.
Kasum. Okay, well, Kasum, hi.
Because that's actually Mohammed and Kashifa's mom.
Oh, fantastic. Okay.
She had a special request there. So, guys, make sure you stay tuned after the break because there's a lot more stuff coming up. So, guys, you don't want to miss out. See you soon. Welcome back, Mindsetters. I hope you've had a nice little break and you've gotten something to eat, to nibble on. You've gone to the bathroom and you've sorted yourself out so you don't have to keep getting up. Otherwise, you're going to get lost. But for now, I'm actually going to just hand straight back to Phil so he can make sure we can get this lesson in.
Absolutely.
Right. Cool.
Okay, thanks so much, Ty. Okay, well, it looks like we're doing quite well on our redox chemistry. We've been talking about electrochemical cells all the time. Now, I just want to show you another way in which they can actually do this. This is the exact same reaction, and Ty's actually posted this up on the page so you guys can see it. They've actually separated out the half reaction. So what I'm going to do is I'm just going to make some notes on here. What they've actually shown on the left-hand side, and this is called an anode. The anode is where oxidation takes place, and this whole apparatus is designed to keep the half cells separate. So in this left-hand side, I've got zinc, which is changing into zinc 2 plus 2 electrons. That's what's happening on the left-hand side in the anode. On the right-hand side, inside the cathode, what I'm actually seeing is that I've got copper 2 plus, and that is my reduction reaction. Copper 2 plus 2 electrons, and that's going to make copper metal. There it is. There's my two half reactions in two half cells. I just want to make you aware that this is another way that they can ask this. This guy is going to be the star of next week's show because we're going to be taking it apart and seeing what all the little pieces do. And we're actually going to start studying, okay, well, where do the ions go? Where does the electricity go? Because this thing is actually a battery, just like the one inside your cell phone. This is the way that most of the portable power, including the one inside Ty's laptop, all of the things which have got little batteries, this is the technology that powers it up. Okay, slightly different chemicals, but what we'll notice is that all of these electrochemical cells can actually do this for us. Okay, but before we say goodbye to electrochemical cells, I'm going to start comparing it to another guy. Now, electrolytic cells, I just want to emphasize what the difference is. Remember that electrochemical cells were all about the spontaneous reaction. Now, electrolytic cells, just like the one in your challenge question, okay, these are non-spontaneous. What you'll actually notice is that you cannot make that positive slope on the redox table. We need to supply the energy into these, and we need to make sure that that reaction happens. So one of the things that you need to do to an electrolytic cell is you need to actually pump the electricity in. You can't take electricity out. Now you might say, why do I want to do this? Well, there's two major reasons. One of them might be that I actually want to manufacture new chemicals, and this is where chlorine for the pool comes from, and where the bleach in your kitchen, and a whole bunch of household products, even PVC, some plastics, are made by using electrolytic cells. And especially for those matrics who are studying things like batteries and chloralkali cells, electrolytic cells are something that you've got to know. And what I'm actually going to do is I'm going to take a look at an example of an electrolytic cell, and I'm going to show you what the difference is. What I'm going to do is I'm going to take the electrolysis of brine. Now, matrix, if you're doing chemical systems, electrolysis of brine is one of the ways that they actually manufacture a few things. So what I'm going to do is I'm going to identify these three things on the redox table. The first species, or the first ion which I've actually got sodium plus. I've got sodium ions. When I dissolve sodium chloride in water, that's what I got. Chloride ions, there they are. And don't forget, aqueous means plus water. There is water all around this. If I take salt and I put it inside water, there's water all over the place. So water can actually be one of the reactants. Okay? So that's very, very important. It's hugely important that you know that water can be a reactant. And in the electrolysis of brine, it actually is the reactant. So I want to see how I can actually predict the products of electrolysis. I did electrochemical reactions, which were spontaneous. Let's take a look at electrolytic cells and see why they're non-spontaneous. So let's go to it. I think Ty might have actually posted this. Okay, now what I've done on my table is I've actually circled the potential reactants. I'm going to show you where I got them. Okay, so now the things which I showed you on the last slide are actually the potentials. These are the guys which I'm considering for the team, and they might be the ones that react. So that is step one. I need to find the reactants. I need to find sodium plus. Notice that I couldn't circle sodium on the right-hand side. Absolutely vital. Sodium plus is very different. Okay, just to show you just how different this is, if I put sodium plus in my mouth, it's going to taste nice and salty. I taste it all the time inside my food. If I put sodium inside my mouth, it's going to blow my face off. It's explosive when it meets the water inside my mouth. Okay, so sodium plus is definitely different from sodium metal. You don't want sodium metal inside your mouth. Trust me, I've never tried it before. I don't want you guys either to. Okay, so sodium plus is a potential reactant. There it is, H2O. H2O is all over the table. I see it on the left-hand side, on the right-hand side. Circle it wherever you see it on its own. Okay, the other one is Cl minus. There it is. And I think my producer's got it on the screen there for you. Okay, so sodium plus and H2O, Cl minus, and 2H2O. Okay, now this is where it gets interesting. I need to figure out which ones are going to be my reactants. Okay, well, how can I actually tell? Okay, the arrows are going to help me out. And one of the things that I'm actually going to see is that my arrows are pointing away from the metal. What you'll actually notice, and we can see, I've got to choose between sodium and water. What you'll actually see is that water is actually the better performer. I actually see that H2O is going to be the winner on this side. What about on the right-hand side? Between H2O and Cl minus, what I actually notice over there is that Cl minus is going to be the winner. Okay, well, let's see what that translates to. That means that my two reactants, there we go, H2O on the left, Cl minus on the right. Now that I've done that, that is actually going to show me how I can make my reactions happen. So H2O and Cl minus are going to be my reactants. Na plus is going to be a spectator. Okay, there it is. Okay, so that's going to be my spectator ion. Okay, and if you're watching this far and you've seen what I've done, you'll actually notice something not so nice. What you'll actually notice is that I can't make a positive gradient. I can't make an upward slope anymore. I can see that this is non-spontaneous. The arrow goes down as you go from left to right. So what I actually notice is that this reaction is non-spontaneous. I need to put electricity in to get it to happen. So H2O, Cl minus, those are my two reactants. Let's see what I'm going to do with them. Okay, so I'm going to keep them up there so we can actually read them off directly. So let's copy them out together. Let's get our marks just for copying. So I read them just as they stand there. So 2H2O, don't forget any charges, plus 2 electrons, there they are. And that goes to make, remember, only one-sided arrow now. That goes to make H2. There's another hint for your reaction. There's another hint for your challenge question. Okay, so H2 is a gas. And then OH minus, there's the other hint. By now, you should be able to solve this, because let's just make sure that's nice and neat. Okay, I noticed that OH minus is coming out, H2 gas is a product, and OH minus is a product. A lot of people think it's just the elements which come out. Okay, now for my next reaction, the reaction which gets a lot of money, and this is one of the ways to industrially produce chlorine. Let's write it out. I chose the one on the right. Let's start there. So there it is. 2Cl minus goes to react to make Cl2 gas. So I'm going to produce 2 gases, and I'm going to produce 2 electrons as well. Okay, now if you followed this so far, these 2 reactions are actually the major reactions which happen inside the chlor-alkali industry. If you've studied this, these 2 reactions are the ones which happen inside the membrane and the diaphragm cells. Very, very important for the production of chlorine, hydrogen, and there's another product as well. And that's dependent on my OH. Okay, so let's check to see if the electrons are balanced. Lucky for us, 2 electrons went in, 2 electrons came out. Let's just label them quickly. The top one, I see electrons going in. Electrons going in on the left-hand side means that this is my reduction reaction. Okay, so that's quite important. The reduction reaction is actually happening inside there, the gain of electrons. Okay, my oxidation reaction over here, fantastic. I can see that the electrons are coming out. There they are. They're on the right-hand side. If electrons are on the right-hand side, means that you've got oxidation on your hands. Let's cross them out. The electrons, I can see on the left and the right that there are 2 electrons. Now let's add everything on the left together. So there they are. There are my 2 reactants, so let's write them all together. So I say 2H2O plus 2Cl minus, and that's going to go to give me H2, which is one of my products. I've got Cl2, which is also a product, and there's 2OH minus. Okay, so there's my 3 products. If you've managed to get this, this is almost exactly the same as my challenge question. Okay, I can actually see that the non-spontaneous reaction is going to produce hydrogen, chlorine, and OH minus ions. Ty, what are the people saying?
So far, they're more just attacking that. They're sticking with this, but they're more attacking that challenge question more than anything.
Okay, that's fantastic. Okay, it means that they're working hard and paying attention.
Exactly, which is always a good thing, which is something we always love to see.
Shall we put them out of their misery?
I think so. I think so.
Okay, well, we got a few minutes. I just want to discuss what's going on inside this challenge question. Somebody pointed out a little bit earlier, there's a little 2 missing, but it shouldn't change what your answer is. A lot of you, I'm pretty sure, are going for option A, and that's not correct. Now, when I do electrolysis on MgCl, and there's a 2 that's missing, so MgCl2, MgCl2, okay, is going to change into Mg2 plus ions and Cl minus ions, and there's going to be H2O. What I'm going to find is that H2O and Cl minus are going to be my reactants. So if you're wondering which one is the correct answer, what I'm actually going to do is I'm going to put you out of your misery straight away and not discuss all of them. I'm going to find that I'm going to make option C, and option C is going to be the winner. So option C, this is not a case of if in doubt, go for option C. Option C there is the absolute correct answer. I'm sure that a whole bunch of you have guessed this. But remember, I need explanation, guys, and I'm going to tell Ty full explanations, because you're not just in it for a calculator, you're in it for the other mindsetters, you're in it to help other people as well. Okay, so I want you to discuss, do you agree with C, don't you agree with C, how did he get that, and where did the H2 come from? Well, I've got to make sure that I actually understand that there's more than just the metal, the anion, and the water reacting inside there. What I'll actually notice is that the reactions for this are exactly the same as inside the electrolysis of brine, which is why I did that as an example. So if you're worried about these notes, remember that we do post them up as a nice PDF file. You can take all the notes and you can study from them if you're making plans to do a little bit of that. Mg2 plus, just remember inside this reaction, is actually going to combine with the OH to make MgOH2, and that's where the magnesium hydroxide is actually coming from. Okay, so magnesium hydroxide is one of those products as well. So I hope that you enjoyed this challenge question. Okay, the challenge question was quite difficult. Some of the clues that I wanted to make sure that people actually understand that electrolytic meant that there was non-spontaneous. So what I'm actually going to do is I'm going to go back to that table and I'm going to show you which one of the reactions that you should have actually been using. Okay, so let's actually clear all of this away. Okay, so that was a spectator ion, that's fine, no problem. What I'm actually going to do is clean up our redox table. One of the tips that I actually give my matrix is that they actually find one of these, they laminate it with some plastic, and you can draw all over it with a highlighter, which is a great way to practice redox. Okay, but now I don't have those ones anymore. What I do have instead is I've got magnesium 2+. I will actually find that nothing has changed. I initially had sodium plus, and now I've got magnesium 2+. There it is. There's my spotlight on the correct reactant. However, I find that water's reacting, Cl is reacting, nothing actually changed. It's still going to be a spectator ion, guys. I think that's all time
we have.
Yeah, absolutely.
Well, I had fun making sure that that experiment stayed far away from me.
Absolutely.
But Phil, I'm sure like you're good to go, everything's sorted out?
Absolutely.
All right, awesome. So guys, I hope you guys had fun. Hope you guys were paying attention. I hope you guys made sure that you were writing notes and you guys had everything that you guys needed from today. Make sure you always just post the page, talk to each other. I will be hunting down the final answer, the person who got it right first, and I will be getting that calculator to you and the labeler. So make sure you keep your eyes on the page. And you know what? By the way, Phil, how did that turn out, by the way?
Absolutely. Okay, well, what I've actually done is I've added a little bit more of the copper sulfate just to bring out a little bit of the brown color from this copper. You can actually see that copper metal is actually formed on the bottom there. It's a nice brown color, and we can see a little bit of leftover blue color, but that blue color has actually disappeared. But guys, I'm going to say goodbye. It's been fun. Thank you and good night.
Yes, and I'm going to experiment and have a sip of that later. Ha! Psych. No, I will not be doing that. But for me, guys, stay safe. Make sure whenever you're doing experiments, you keep it safe. But guys, I'm going to say bye. Peace.